Good morning. Good to see you. Welcome back to ACM1. I hope you don't own too many of the wrong stocks today, and I hope they go back up real soon. I hope you're, yes, right. So are you ready for a big day? Yes. Tell you what, let's take attendance. Let's put up the seating chart. Let's get the wands, the paddles, and try to find yourself on the seating chart just to be sure you know where you are. And now, please, if you have been to the expo, to the ACM1 expo next door, would you please show green to the front? Show us green if you've been. And excellent. And those of you who have not been to the expo, I urge you to do so. It's right outside. It'll be open till 4 o'clock today, and I guess your big opportunity to do that is not to walk out on the upcoming speech, but rather to go during the 2-hour lunch break from 12 to 2. Now, too many of us still tend to think of computers as data processing machines, or we tend to think of the internet as an email box of some kind. But at ACM97, Brand Farron expressed an entirely different view.
Every time a significant storytelling technology has been introduced to the world, it changed the course of civilization, or rather, we changed the course of civilization with it. And this can be language, it can be writing, it can be printing, it can be radio, television, it can be poetry, it can be animation, and now it's getting to be computers.
Now, no person that I know understands what Brand is talking about better than Alan Kay. I first met Alan in 1972 at the Xerox Palo Alto Research Center, where he was busy down the hall inventing personal computers. He had previously graduated in mathematics and molecular biology from the University of Colorado and received his PhD in 1969 from the University of Utah. Alan is best known for his ideas about personal computing and the intimate laptop computer, and his inventions of overlapping window interface, modern object-oriented inventions of overlapping window interface and modern object-oriented programming. Believe me, I do not want to get into a fight about who invented modern object-oriented programming. His interest in children, of course, in children and education, were the catalyst for his many, many ideas. Today, Alan is the Vice President of Research and Development at Walt Disney Imagineering, where he is a Disney Fellow. A former professional jazz guitarist, composer, and theatrical designer, he is now an amateur classical pipe organist. Today, Alan will attempt a lifetime first. He's told me that he has never given a talk in less than 30 minutes. Please join me in welcoming Alan Kay.
Thank you. So we're here looking at the future, and many people have pointed out that some decades ago, nobody knew what the future was going to be, but of course that wasn't so. There was a very good roadmap of the future back in the 60s in the ARPA community, a dream going all the way back to even the late 50s about a worldwide information utility, and the start of interactive graphical computing with Ivan Sutherland in the early 60s, 1962, and that very same year, the machine I think of as the first personal computer, which is Wes Clark's Link. In 65 was when Gordon Moore's first article in Datamation appeared, putting forth Moore's Law. And so by the time sharing had happened by then, and people were starting to do interactive computing. And so there were a lot of components there that made it very easy to predict that personal computing was going to happen. A year or two later, flat screen displays started to show up in laboratories and so on and so forth. And I think the difficult thing for most of the people back then was that they were trying to be practical. The reason they missed predicting the future is that they were trying to be incremental on the infrastructure that existed rather than being romantic about what it would be really neat to have and what would be especially good for children to have. So I'm going to talk a little bit about why the computer revolution hasn't happened yet. But first, if we could have the computer screen. One of the things that always happens in talks is the people behind all of these ideas never get their due. So I just made this complicated panoply of influences on us, of cognitive influences, computer influences. Here's our group. Here's some of the people we work with. Here's our interns. And in the background, we have an open source community, courtesy of the internet. And so I guess the right title for this slide is that science is a great open source process. It was one of the original open source processes, and you actually make progress by giving your ideas away. We wouldn't be where we were if science was a closed process. Business people have not learned this yet. If they want to make money, there has to be, Bob Noyce used to say, engineers make wealth and everybody else just moves it around. So, to me, the way I think of the future is I don't even worry about the technology. And there's a nice suggestion here by Marshall McLuhan that children are the messages we send to the future, but not exactly. They really are the future we're sending to the future. There isn't anything else that's much interesting about the future except the people who are going to be there. And so helping children grow into the next several generations of adults is the most important thing we can do. And if we go to graduation at one of the nation's greatest universities, Harvard University, about 10 years ago, right after the seniors flipped their tassels, NSF took a camera around and interviewed a number of them about a few simple ideas about the world. And so let's hear that.
To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happens because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun. And it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
I took physics, planetary motion, and relativity, and electromagnetism and waves.
I've never really had a scientific background whatsoever, and I got through school without having it. I've gotten very far without having it.
I had quite a bit of science in high school, yeah, through physics, first year, and 2 years of chemistry.
Regardless of their science education, 21 of the 23 randomly selected students, faculty, and alumni of Harvard University revealed misconceptions when asked to explain either the seasons or the phases of the moon.
When it's further away from the sun, then it gets colder.
The Earth's position interferes with the reflection of the sun against the moon.
So we can see that the main curriculum at Harvard must be Confidence 101. But of course, it's not just restricted to Ivy League colleges. I was waiting for NSF to ask the next logical questions, but they didn't in this wonderful video. You can get it over the internet, called The Private Universe. And but a couple of weeks later, I was at UCLA and found that the audience for the talk I was giving there were mostly graduating seniors. So I asked them to come outside with me, and one by one I asked them the same 2 questions and got about the same results. About 95% of them had serious misconceptions about one or either. And then I got to ask the next question, which was, well, tell me this: if the proximity of the Earth to the Sun has something to do with the seasons, then tell me, do you know when it's summer up here in the northern hemisphere, what season it is in the southern hemisphere? And every single one of them knew that it was winter. They didn't know why, obviously. But it was odd, so they'd remembered it. And I think I'm justified by induction to claim that the Harvard students and this professor here all knew that. Then there was about a 30-second pause while I watched each of these people struggling with this fact that they'd had in their head conflicted completely with their proximity theory. That was one of those sort of, And for this professor, the question for those who are confused about the phases of the moon, I'd ask them, well, have you ever seen the sun and the moon in the sky at the same time? And actually, anybody who walked out the Fairmount this morning, anybody do that? Moon is right there. Was it in phase? Anybody see it? This is my favorite thing, because people have seen this zillions of times. And the moon was visible in the sky, and so was the sun, and the moon was in phase. And therefore, it is very hard to imagine how anything could be between the sun and the moon if you can see them both in the sky. So, now what's going on here, variety of things, but most important thing for this talk is that these Harvard kids were just thinking normally. They're doing absolutely normal human thinking, which is to compartmentalize the knowledge, make each one into a little story, and so forth. And this is basically the future we're sending to the future, and mostly have been for the last 80,000 years. Basically cave people, now they have atomic weapons. And if you take this common sense way of looking at the world that has been around for many tens of thousands of years, let's pick on Yale this time, give this guy a Yale diploma and dress him up a little bit, he can go very far in most people's estimation. And sure enough, a couple of weeks after Bush took office, he started bombing Iraq just to show them that he had a spear. So in this case is a missile. And this is basically what's going on. So it's very easy to predict the next 50 years, and that is, for most people, it's going to be just the way it is right now. There's going to be more glittery things around, more distractions. But as Neil Postman pointed out, that people in the 20th century accept more things on faith than they did in the Middle Ages. Because most people accept all the things on faith that were accepted on faith in the Middle Ages, plus there's all that new science stuff that most people accept on faith, and all the new medicine that they accept on faith. So for most people, very little has changed except things in the environment. And of course, I really was looking for modern uses of spears today, and I was going to go on the internet to find it, but the LA Times last weekend blessed me with a front page article on the revival of headhunting in Borneo. And here are these guys, they're on motorcycles, but they have their spears, and they actually have beheaded at least 500 people now. As it says here, they are using traditional weapons to defend themselves and send away evil because it disturbs the harmony of life. And they eat their hearts to subdue their victims' spirits and absorb their magic. This is perfectly normal behavior. It's been going on for tens of thousands of years. Just let me go back here for a second. And the thing that struck me as worse was another article in the New York Times, which reminded me that slavery still exists many places in the world, including this recent thing that came up, these little paper clips that all of us use are made by slaves that were purchased from a woman's prison. This is going on today, and there are many aspects of slavery going on all over the world as I speak here. So, pretty frightening. Sorry. So one way of looking at this is McLuhan's way of the goldfish in the bowl. Said I don't know who discovered water, but it wasn't a fish. We are the fish, and the pink water that the fish can't see are our underlying assumptions about the world, our deep beliefs. And you get a model of thinking that Arthur Koestler came up with is if you take the pink water in the bowl and make it a plane, here the ant crawling along is like human thought, having the illusion of making progress, being able to set goals, get around obstacles, and so forth, but never being aware that it's doing a flat set of pink ideas. Of course, every time, once in a while, a little blue idea comes along, but we've all gone to school. Many people go to church. We all have parents. So there are powerful forces to kersplat those little outlaw ideas. But every once in a while, you're taking a shower, out for a run, and one of these epiphanies comes. How many people have had one of these big epiphanies? Feels like it comes from the heavens because it was in our subconscious, not in our conscious. And the old days when people had these, they'd go out and start a new religion because it does appear to come from the heavens. But we know today that most ideas, wherever they come from, are mediocre down to bad. And so it's very important to be careful about these ones that seem to come from heaven, because they're likely to be bad ideas as well. And Koestler pointed out that you get a mixture of emotional reactions when this happens. If it's a joke, you start laughing. And in science, it's an aha, which you may also laugh about because, of course, the world didn't change just because we got to see it a little better. So all of these things we found out about the world are lurking beyond our ability to see them. And then the most important one is this long, drawn-out awe of art, because one of art's main purposes is to remind us that there's more to be thought about than is currently in our little pink context. And a lot of the way of getting from the mundane world to better, different ideas is through artistic thinking. I think Bill Buxton will say a few words about that as well. To me, it's the number one important thing to think about when you're trying to send children into the future in a more enlightened way. And that is to develop every child's initial aesthetic approach to the world. And then the kicker for modern education of invented ideas is that it takes almost as much creativity to learn one of these ideas as it did to invent it in the first place. And this is where school is completely wrong, because school is basically set up to teach stuff that's fairly easy for kids to learn. And the problem is most of the important ideas to learn now are not easy to learn, and so we have to find a way of getting the kids to be creative enough to break out of their little pink planes. Here's our friend Betty Edwards, who teaches drawing to people. And one of the things she does in the very first day of her class is say that, the problem with drawing is not that you can't move your hand, but you're already interpreting what you see too much. So she shows them these two tables, and she says, this table shape, top shape, is exactly the same as this table top shape. And everybody says, no, that can't possibly be true. And she says, well, look, I'm going to take this guy off here, and I'll rotate it, and I'll just pick it up and take a look at that. It's even amazing if you just bring it over here. It is very hard to see that this length was exactly the same as that length. And that's another way of thinking about what our problem with the world is. And the Talmud points out we see things not as they are, but as we are. And I've often wondered what happened to the person who came up with that idea in an Orthodox faith. Because if you take it to its logical conclusion, it's not where the Talmud really wanted to go. So Montessori had this great idea. She pointed out that children are set up to learn in a village culture through play, imitation, and the problem with 20th century, now 21st century knowledge is that most of it is opaque to children, unlike the knowledge in a traditional culture. And so her idea is we have to give the kids modern environments and modern toys where the kids accept these toys as play toys, but they have interesting side effects. And she spent many years of her life designing toys designed to be pleasurable for the kids and to have worthwhile side effects on their common sense. And one of the main tasks we have is to ask ourselves, what are the 21st century thinker toys going to have to be in order to get this uncommon sense, as Montessori put it, that she was trying to shape. And again, the root there is through art and this ah-ha-ha combination of breaking through the pink plane to the blue plane. Well, that's a little background for what we might choose as some goals for making a future. And I got involved in this stuff through no fault of my own, I believe. Ed Cheadle and I were working on this desktop machine back at Utah in the 60s. 1968, I visited Seymour Papert, and kids were doing programs like this. They would make a circle with their body, and then Seymour would ask them, what are you doing? And they'd say, well, I'm going a little and turning a little over and over. Type that into logo, forward 5, right 5, repeat it over and over again. Execute it, and you get this perfect circle. No x squared plus y squared equals r squared. The reason is that the turtle is a vector, and this is a differential equation in inertial coordinates, which is the language of differential geometry, which is the main language of most hard sciences today. And here were these kids treating this as a toy. Logo is a toy. And Seymour was not trying to teach them calculus. He was trying to do what Montessori said we should do. For young kids, what you want to do is to teach them the intuitive background for modern knowledge. Give them a big tree with lots of branches to hang these more crisp ideas on later, but build that uncommon sense tree while the children are young. So I thought this is the best idea that I'd ever seen for what a computer might be good for, which is to help children grow up thinking better than most adults do today. But of course I realized there was a Zen problem here. Even in 1968, programmers were kind of the least enlightened people I knew. They could take this beautiful silk purse of a computer with all of its possibilities and turn it into the sow's ear of most software. And if anything, that has gotten worse today rather than better. So that made me think of the computer being kind of like a piano. You can put pianos in every classroom, but the music is not in it. It's an amplifier of musical impulse in a person. And you can develop that musical impulse in a person without a piano or any other musical instrument, because we already are musical instruments. And then these wonderful instruments that have been invented are amplifiers of these musical impulses. So the Zen is something, it's like there's a Zen in music. The Zen is not in the piano. The Zen has to be developed. It's in humans, has to be developed, and then we can amplify it with various kinds of technology. So coming back in the plane from Utah, from that visit, I started thinking about a kiddie computer and realized it could not be a desktop computer like the Flex machine because kids are mobile, and I had this image of them taking it out like we take out books. Books are nice because you can take them out and think your own thoughts with them. And so this image of two kids learning science by programming a collaborative spaceboard game was kind of the first image I had, and taking the Dynabook to the tide pools and this notion of an instrument whose music is ideas. And of course, music is an idea, so music had to be part of this, and so forth. And then I was wondering whether we'd ever get done before we died, because if we look back in history, there was a great technology invented around the middle of the 15th century here called printing, but the real printing revolution really happened in the 1600s, so it lagged by about 150 years. The biggest changes from the printing press happened here when people gradually had learned how to argue in a very different way and think about what knowledge meant in a very different way. And both science and the social argument that led to various democratic revolutions happened in this period of time. And so the mainframe was kind of the manuscript book, only ownable by an institution. And so we had these ideas of desktop computing and then these intimate laptop computers, we call them today. And I was wondering how much of a lag is there actually going to be before the real computer revolution happens? Because if you look at this as being the real printing revolution, it required a rather large number of people to learn how to read and write and to be conversant with the powerful ideas that could be best expressed in a book. So it's not a question of making the possibility of it here. The Gutenberg Bible was set up to look as much like old manuscript books as possible, so as not to scare anybody. One of the major uses of the printing press, besides printing Bibles back then, was printing indulgences for the Catholic Church. So it was an early form of paper money, actually, because indulgences were traded back and forth as currency. So there are many mundane uses of printing back then before the real stuff kicked in. And I would claim that what's been going on, especially since 1980, could hardly have been more mundane. It could hardly have been more of a caricature of what people were thinking about in the 60s and 70s. So, short talk, can't go through all of the goals you'd like to have here, but one way of thinking about this stuff is that because of the way our minds work, minds are little language machines, everything comes to us filtered, and it's kind of like a shadow show. For instance, gravity, let's say, is the real bunny out here, casts this shadow, and Newton's theory of gravitation is expressed in mathematics, which is kind of like making a shadow out of your hands. And we try and get it to cast as similar a shadow to the bunny's shadow as possible. And it worked for a long time until somebody noticed that the real bunny had a little round tail on it. And it was hard to make a little round tail with your arm being in the way. And so Einstein, in order to get that little round tail on there, had to go to a completely different way of looking at gravity and a different set of mathematics, which if you only looked at this part of it, gave you a nice Newtonian bunny, and then it had this extra stuff on here as well. And it's important to realize that you can put on a fun shadow show without making anything representational. Language is about language, not about the real world. And Einstein really realized that, and he said a number of wonderful things. One of my favorites is you must learn to distinguish between what is true and what is real. What is true is what you can do in mathematics, and what is real is out there. And as he said, as far as mathematics refers to reality, it is not certain. And as far as math is certain, it does not refer to reality. And so this, I believe, is the modern view of science, which is that science is a negotiation between the limitations of our representations and what our brain can make of things and the kinds of probings we can do out there. And the important thing about this is one of the greatest heuristics for making progress in all areas that has ever been invented. It's just the knowledge that you're only dealing in maps. And therefore, in order for the map to work, the map has to have criticisms about how well it is doing it. It has to be scaffolded. And Korzybski, 50 or 60 years ago, said that one measure of sanity is the comparison between what's in here and what's out there. And by that measure, all humans are at least unsane. And some of us are quite dangerously so. And so an interesting global goal for sending children into the future might be to send them into the future a little less unsane than the adults that occupy our world today. So these are all thoughts from back then, and a few years before I'd gotten my particular slant on what I called objects, which were a biological approach to computing. And the simplest way of thinking about it is the idea is computers all the way down. It was influenced quite a bit by some of the thinking that was going on about the ARPANET, having networks of computers, many, many computers. And at some point I realized that if you only had little software computers that were made out of only little software computers, you'd have this great way of always retaining full power on all of your representations. You'd never degenerate to a data structure that had to be interpreted from the outside. That these objects, when you sent them over a network, would take their main interpreters along with them, rather than being these raw packets of bits that somebody would have to write an interpreter for at the other end, and so forth. This is because my background was in molecular biology. And Sketchpad had already started using ideas like that, and Sketchpad 3 had already had multiple windows. Multiple windows go all the way back into the early 60s. So there are a lot of ideas about using this, and if we come up to the present and take a look at modern objects here, 2001, a lot of different things here. So, you know, a movie is an object in this system.
At first I was afraid, I was petrified, kept thinking I could never live without you by.
I love her, but I have to move this talk along. Little game is completely made, everything in here is made out of objects. This is a little Pong game. We can move the paddle and so forth. This 3D bunny is sitting on what looks like a 2D desktop here. So if I set the bunny loose, see it actually comes out in front. It's a little hard to see exactly what's going on until the bunny actually starts going behind. Now you get a better idea of the relationship of 2D and 3D space in this system, is that they're actually intermingled. And if you think about it, why not? You don't want to be slaves of a desktop. Another interesting way of looking at it is this thing we're all familiar with, which is word wrap. But what is going on back there? In this biological way of looking at things, these letters are actually little objects that are like little animals. And one of the things we've taught them is to follow the leader in a couple of different ways. So this way, when I say, do your thing, only the letter capital H knows what to do. Everybody else has to follow. Kind of cute. It's nice because this is a program that kids can figure out because it's basically holding the hands and following. You notice that these guys are active, so I can bounce them around with the margin here. Now, more direct way of programming this is to not move until somebody has called to you that I'm in my right place. So the H will go there, and now everybody's stopped until they know that they can go, and they go. So that's kind of cute. And if we do it all behind the scenes, we get this fiction of instant thing. And this is just typical distributed algorithm in a real dynamic OOP system. Okay? So another thing you can build out of these are overlapping object interfaces. Here's a little recorder morph here that's going to, so we can record demos and so forth. And I've just got it turning this guy back on again because I want to show you a way of thinking about the abstraction of this. If every object has the same DNA, then there really must be just wearing costumes. And this little mouse up here is a button. If I click on the button, I'll reveal what's actually here, which is each of these types here is actually made out of one type. And the abstraction here we're showing is just what their boundaries are. And if you have a dynamic object system, you can also count the objects. So I'll execute this program here and say, please count all the objects there. And it says there are about 750,000 objects in this group of things, part of which is this demo. Okay, so basically a universal algebra, if you like mathematics. And the way we divide it up is one language. So it's like if a kid learns English, they're learning the language of Shakespeare, but they might be 10 or 15 years away from being able to appreciate Shakespeare, but there's a continuity of using language for talking about a whole bunch of different things. So in this system, which is called Squeak, which is derived from the work that we did at Xerox PARC, there are basically 3 views of this single language and single system. And the operating system, which this has its own, is written in the same language that the kids do their programming in. That brings us to kids. We've been working with many thousands of children over many, many years. This is the hard part of the research because the average educational experiment doesn't go right. And whether it goes right or wrong, it is very, very hard to tell why. So longitudinal experiments over many years are necessary to get even the simplest amounts of information. And basically what I'm going to show you a little bit today in these examples are some of the things that we do with 9, 10, and 11-year-old children. So we start off with a blank slate. If a kid is getting this on the internet, they get a set of hints. But the learning here is actually by doing construction. And each one of these things is like a little 3 or 4 minute project with lots of reflection. I'm just going to run through some of the things. So I get a little palette, drop it in to get a painting. And the first thing I'll do is kind of the quintessential project here, which is a little car that you can learn how to drive. Design a car as seen from the top. Both boys and girls love putting on big off-road tires when they do this. We don't give the kids clip art because it's very important for them to learn how to draw. This is more of this art and play. So the kid makes the car the way they want it, and it immediately is made into something that they can do things with, and they can look at another view of it, which is its symbolic view. And the Montessori game we're playing here is that here is where the kids' main payoff and interest is, and what we're trying to do is show them, build their intuition as to how powerful it is to be able to have some symbolic ways of expressing behaviors of these things. So if you look at Sketch's heading over there, let's call it car. Click on this little caret, so the number starts counting up, the car starts rotating. And again, if I rotate it with my hand, the number goes positive and negative. So these are 2 views of the same thing. Here's a car forward by 5, so I'll click on the exclamation point. Car turn by 5. Then things get fun when you can just drag out these little behaviors, and it makes a script for you, and you can just start the script going. And all of a sudden, I've got basically Seymour's logo turtle circle with a costume on it. And this costume is very important for many of the kids because it enables them, as Bran Farron was pointing out, it enables them to get into this stuff, into their personal story about something they want to do, like being able to drive an adult car. Okay, so then what we want to do is to make a steering wheel for this. This is like old-time Lego in that the system doesn't know that I'm making a steering wheel. I'm just making a drawing as far as it's concerned. So I say keep. Same deal with the steering wheel. I can look at its interface. Looks exactly the same because the DNA is the same. I'll call it steer. And it has a heading as well. And now let me do an experiment with driving this car. So let me click this number down here to 0, and I see the car is going straight. If I go negative, the car is going the other way. So if I can put positive and negative numbers in here, I should be able to steer this car around. And steer's heading there is generating positive and negative numbers as I turn the steering wheel. So why can't I just pick up the name of those numbers and drop them right into this little script? And now can I control the car by driving the steering wheel? And I can. The kids love this for about 30 seconds, and they complain. They say, wow, this is great, but it's too hard to steer. And we say, yeah, it's because you made a race car. And they say, what's a race car? And we say, well, there's no gears between the steering wheel and the front wheels. And the kids say, well, what's a gear? We say, look at this little triangle here. Press on it, and you can go and do a little arithmetic. Let's divide the number coming out of the steering wheel by 3, and now the car should be easier to control. And it is. So just to pause for a second, the kids have learned a few powerful ideas without even giving a name to them, including why divide might be useful. It's useful for scaling things. And you have to realize that in a 5th grader's life, they've never had a use for division. Think about it. You don't need it for dividing up M&Ms. You do that by parceling them out one. You do pizza cutting by eye. So nowhere in the 5th graders' basic way of meeting the world do they need any of this stuff until they start using a computer. The computer is actually allowing them to make their toys behave the way they want them to. Okay, so let's stop this guy. And let's paint ourselves a road. Get a brown road here. Now, one of the things the kids do is to make a game to put their car on the road and see if they can keep the car on the road, and they can make noises if the car is getting off the road. And they actually get in one of the classes that it's used at the Open School in Los Angeles, they get a little driver's license if they can keep their car on the road. So this is the ultimate enfranchisement in adult-type activities. But the next phase is what I'm going to show you here, which is I want to make a little robot car, explore another powerful idea. So I'll repaint this car, and I'll just give it a little sensor. And the sensors are just paint. So this car has a little sensor. And now I want to make this robot car. So look at its viewer. And first thing I know I want the car to do is to go forward. And I want to test the road, so I get a test guy here. I'll look at tests in here. Here's a nice test. So I'm looking at car's color blue, which I'm going to use as its sensor. And I'm looking to see if I can see the road, which is this brown color. And I know that I am going to do a couple of turns here, but I'm not sure which way yet. So I'll just drop a couple of these guys in here. And let's think about it for a second. So if I'm following a wall and I bump into the wall, I should turn away from it. And if I'm away from the wall, like I am here, I should turn into it. So this says the no version of the thing is right. Car turn by 5, turn clockwise into it. And I should make this guy -5. So I'll turn away to it from it when I hit it. And let's start that going. And so this is one of the simplest feedback programs. And feedback is an incredibly powerful idea because it's one of the main ways that both nature in general and humans in particular make progress when they don't have complete information. So this gives you a search. And there are many different parts of the curriculum that we do that involve these feedback ideas. Okay, so I'll stop this guy and move it aside. Now let's take a look at another use of stuff here. I'll spare you my drawing these ants. So I draw these two ants with their legs in different positions, and I drop them into a thing called a holder. And now I want to program an animation here. So I want the car to look like something. Starts off with car looking like dot because I haven't said what it should actually look like. And let's look at this holder here. And here's the ant. Holders, player at cursor. Here's the ant right here. So let me drag that guy out and drop it in here. So now I've got car look like holders, player at cursor. And if I click once, the car now looks like this ant. Now I want him to look like the other ant. And here's the control of the cursor in this holder. And I'm just going to say increase by 1 over and over again. And if I start that going, I get my ant animating. So there's many different things you can do just with animation there. And of course, he's still this guy here, and we might ask what would happen if we turn on our road following script here. So I'll turn this guy back on. And now we've got an ant following a scent trail, or something we can make into a fish swimming upstream and so forth. Okay? Turn these guys off. So what I'm doing is just taking you through some of these sort of first stage powerful ideas. I'll get rid of this road. Here, drop this down there. And now what I want to do is to, let's see, this guy first. I'm going to make a particle system here. Drop the ant in it. Take this little script out here. So what I'm going to do is, again, I'm going to repaint this ant, but this time I'm going to get rid of everything except the little blue dot here. So that gives me a little blue dot. And now let's program this dot to do something. So forward. Let's make it forward by 15 so it moves pretty quickly. And let's make it bounce off the walls. Now these bounce will make a sound when it hits the wall. I'm going to go to the teacher's favorite sound, which is silence. And you'll see why in a minute. So if I start this guy going, just going to bounce around here. And now what I want to make is a zillion of these. So I need a copy command here. And copy, I just copy it, I'm just going to get a stack of these guys on top of each other. It's not going to look all that exciting. So what I'm going to do is actually turn the guy each time before I copy it. And what shall I turn it with? But I'll turn it with a random number here, some number between 1 and 180. And then if I just hit the exclamation point here, I'll spritz a whole bunch of these guys out there. And so I get a little particle system. Okay. Now I'll get my little, there's a million things you can do with a particle system, and I'm going to show you a couple of them later. This one's kind of fun here, which is a Feynman motor. So I turn these guys on. So this ratchet guy is going to go one way when a blue dot hits the red, and it's going to go the other way when the blue dot hits the green. And on average, it's getting hit. You know, see, it's sort of tipping around a little bit. But if I turn one of these guys off, it's the equivalent of putting the pawl in the ratchet. So I'll do that. And now the pall prevents it from going clockwise. I'm only going to get counterclockwise. So this is a thing that Feynman put in a paper called There's Plenty of Room at the Bottom, where he's trying to explain how everything interesting in most phenomena, including biology and chemistry, ultimately depend on there being kinetic energy from heat. Let's take a look at some of the kids. So those are kind of 4 powerful things you can do right away. Now, when you look at kids' projects, you notice that they're a little different. They almost always put idiosyncratic art. They don't copy our art. So here's Lauren has fixed this thing so it warns her by making she's much better at driving this than I am, but basically her idea is if this was giving her sonic warnings, then it would help her learn to drive the car right down the very center of the road. Now, these 2 girls were less confident than many of the other kids in the class, and the challenge here was to figure out a way of getting a robo-car to drive down the center of the road. These 2 girls came up with a truly elegant solution. And the way we explain these things to people on the internet, because everything I'm showing you here is directly internetable and is going out on our website called squeakland.org. We use these transparent membranes here to overlay the kids' program. So when a teacher is reading this, they can come in and say, oh yeah, here's the car, here's an explanation of it. We explain to the teacher why the program is elegant, if it is elegant. This one is truly elegant because the kids realize that instead of having nested conditionals, it could be just 3 separate cases. And this thing is actually running right now, but this conditional says don't run unless you're on the road you're supposed to run on. So if I pick it up and put it on the road, and notice that when it gets off the road, it will not run until it's made the turn. And the car will still do the right thing if this sensor hits all 3 things at once, because the 4 and the -4 will cancel out and the thing will just go forward. So this is, when you see a child derive a program like this from scratch, it's worth the 30 years, because this is wonderful when they do it, and it changed their entire attitude, as you might guess, about whether they could do this stuff. Here's another kid that realized that cursor increased by 1 was wrapping around, and therefore you should be able to have as many frames as you want in the animation, and why not put faces on them? Here's another kid who realized you should be able to do the drive a car and the animation at the same time. So here's his Superman animation here, and here's his forward, and he decided to put in a speed control. So the forward in the joystick controls velocity and side by side. So he's got something more like a video game here, and made a maze that you're not supposed to bump into. Okay, now these, when I said we have a magic new algebra, this is partly what I meant, because we have been doing increase by all along. Increase by is how you move around the physical world. All of these guys are vectors, and you're adding a little vector to them, and so they move. We were doing increase by when we were doing animation, but we're jumping from one part to another in this holder structure. And here we have another holder structure that is actually holding sound. So just to show you a little bit, so if you take out this magnifying glass, you can see each one of these things is a little guy like one of the ants. And it turns out that sound synthesis is just moving a speaker cone according to the height of these separate guys. So this very same animation algorithm should work if I am moving the speaker cone instead of changing costumes. So if I turn this on, so here's and the real speaker cone is actually doing this, but of course it's going so slowly that all you're getting is a deep bass, far, far too low. So what I want to do here is go in here and speed everything up by a factor of 10,000. and play it.
Tom.
And I can ask the question, what would happen if I put 0.5 in here? So it goes down an octave. And what if I put another number in? The kids now realize that this little number, which is the rate of progress through there, is the magic number that they need for every note on the keyboard. And so by making a little button that has these magic numbers in there, which they find out for themselves, they have suddenly made themselves a sampling synthesizer that works just the way the Roland synthesizers do. And you can combine this into a really neat musical thing. So this, if you look at the trombone sliders here, when I move this trombone player, so it gets louder when he comes to the front. Bring the trumpet into prominence here. Actually, I used to play in a Dixieland band, and I like flugelhorns. So I'll go in here and I'll change the trumpet. Make the clarinet sound more like a clarinet. I'll explain what I'm doing here. This is real-time FM being controlled. I'll stop this for a second. If we can't hear a C in our head, we can go in here and it will be played. If I play in the score here, near a note, I'll get the whole chord. Well, that sounds almost Dixieland, but I know that this wants to be a seventh chord, so I'll just change this note in the chord, get the seventh chord. I'll change the rest of these guys. So the progression is now like this. Start it up again. So these synthetic timbres that the kids make can be inserted into this. And if you want to see what the little toy program for doing all of this is, it's these scripts. So these 9 scripts are all that has to be written in order to do this play environment. Okay, science is more tricky on a computer because you can lie on a computer, and business people do all the time. You can have inverse cube laws of gravity and so forth. So in order to do the real world, we take a fake picture of the real world, like this sketch of the Imagineering building, and we superimpose a movie on it. So if here's one of our cohorts here dropping a water balloon, and it's kind of hard to see what's going on, even in playing the movie over and over again. But if we look at every 10th frame, we can see that something nonlinear is going on. And one of the things that's beautiful about having these pictures is that we don't even need numbers to figure out what is going on. So there's the height, is the distance between the two balloons, between those two frames, and I can see right away here that I somehow have to make this higher by some amount in order to get to the next balloon. And I somehow have to make it higher by what seems to be about the same amount to get to the next balloon. And if I stack these up, and if I've done this carefully enough, here's my little incremental amount that looks like it's the same. So it looks like what's happening is the velocity is increasing at a constant rate each time interval that I've been looking at here. So in order to check that out, we build ourselves a little model. And again, I won't go through building the whole thing. I've just prepared a little set. And the little model winds up saying, I want to increase this thing called velocity by -1, so that's the constant amount, over and over and over again. So velocity will go up uniformly, and I want to increase the balloon's position by whatever this velocity is each time. So the balloon's position is going to change non-linearly, and I can test that out by trying them both at the same time. And I see my time constant is off a little bit, but I believe you'll trust me that if we monkey with that number, we can get them to match up completely. And that allows us to put gravity on objects of pleasure, like a spaceship. So if I start this guy off with just the gravity going and try and land him on the moon, I get an explosion. So I have a motor in here. I have something that will show a flame when the motor is on, and I have something that will crash me if I don't land at the right speed. So now let's see if I can fly this ship down. But I have to be careful because my motor is powerful. It'll come back. Sorry. So I do it carefully enough. Well, now my blood is up. There we go. All right. Can still play a video game at 60. Okay, so here's another kind of a feedback idea, a more profound idea, which is following gradients. So we have gradients here, and here's a salmon smelling its way upstream. So what it's doing is it's comparing the brightness under it to where it was last time, and unless it's in an upstream direction, it circles until it finds a favorable gradient, then it follows the gradient. Here's a clownfish which wants to find its sea anemone by the gradient of perfume given off by the sea anemone. So that this is a radial gradient. So I'll start him going. And you see you need another This is kind of like business. You know, they're following gradients, but they don't have a strategy when the gradient runs out. Same thing with the salmon. He's going to circle around. He's actually gotten close enough to switch over to another brain module that will get him to nest in the sea anemone. Okay, now a little more science. Diffusion. It's really great. If I had time, I would do it in this audience because I love big audience. We have to turn off the air conditioner, but if you open a fairly powerful perfume, now you're seeing it going 60 times real time, and to ask people to raise their hands and they can smell it, you get this beautiful diffusion wave going back into the audience. It will go at a different rate depending on how hot the water is in here. And now we're using a sort of a much more powerful built-in particle system that we derived from Mitch Resnick's star logo stuff. So here's the water particles and here's the dye particles. And this is a very, very simple little program for each guy, which is to be bouncing randomly off these guys. And we see what happens as we get disorder that starts becoming quite uniform. And that's a very nice motivator for thinking about what might be going on down there. Now, if we combine gradient following, we can do some really cool ant stuff. So we have about 50 ants here. These guys are food. And the ants go about randomly until they find food. They have food, they will go towards the nest and leave a pheromone trail behind. And notice the pheromone trail organizes the other ants as they wander into it, because if an ant wanders into it and doesn't have food, it goes upstream to find the food and then downstream to find the nest. And you can think of these as fads. So it's really quite interesting to watch. Yeah, so here we have quite a bit of activity and there's no food. This is kind of reminds me of investing. the excitement lingers long after the food is gone. So there are many beautiful things you can do with these particle systems. And fifth graders have difficulty with recursion, like most of us. And one of the interesting things you can do with objects is you can do programs that would normally be done recursively by making new objects that just do something once. So to grow a tree, what you really need to do is just grow one branch and then make two buds and tell them to do the same thing. So if I tell this to happen, there's a little bit of randomness in there. It's all done in parallel. And over here, we have it at a much greater depth. So it's actually putting out about 2,000 little particles here. A little randomness, and you start getting an idea that nature, though complicated, is complicated in a very special way. It's not complicated the way we think most things are complicated, and therefore it can be understood in many important ways. Okay, now to end up, look at our last particle system example. There are lots of wonderful things you can do with kinetic theory of heat and everything, but suppose these are people, and we're going to infect just one of them and let the infection spread. Get an epidemic. People always root for the last one. There it is. That's life. Or death, depending on how you look at it. Hard to see what happened there, so you want to get a little graph. You should always do a few of these things that have random behaviors. Okay, another graph here. So these are characteristic curves of AIDS. And it's quite interesting if we just change the time constant by a little bit here. So the linear path along the side is about half what it was. If we started an infection here, we see it happens right away, and we get something that looks more like typhoid with just a little change in the time constant. And the problem here is that unaided human common sense has a keyhole only about this big, and if you look at AIDS with normal human common sense, it doesn't look like anything needs to be done. Whereas if you come up here and look at typhoid, you can see right away that something needs to be done. But science can look at something like AIDS before it's truly dangerous and boost our common sense. This uncommon sense of science is what allows us to imagine things deeply enough to take action as though there was an actual epidemic. And that's important because actually 22 now have died. 35 million are infected in sub-Saharan Africa alone. Some people don't even still believe that AIDS might be caused by a virus. The politicians haven't taken action. And it's starting, 70% of, for instance, Botswana land is infected now. 70%. So we're talking about 2 Holocausts already, and probably 5 or 6 more Holocausts to go before this gets controlled. And yet it was controlled very well in the countries that had science, because they knew that no matter how long the time constant is, that when you have a deadly disease that is contagious and incurable, you're going to get an exponential curve that is going to be very, very dangerous. And so I've ended where I began, which is if we want to have a great future, let's send children to make that great future that think a heck of a lot better than most of us do today. Thank you. I did. How long was it? Is it okay?
Alan, I'm sorry to say that you did not break your 30-minute record here today. So I have time for one question. Kay's first law that I've read about is that the best way to predict the future is to invent it.
I've heard that.
Yes. And Kay's second law is, as I understand it, is that to win big, you have to invent something that creates a need and then fills it. What is Kay's third law? And while you're at it, what's your fourth, fifth, and sixth laws?
Well, I don't believe in laws because that's the whole pink plane, blue plane thing. Is the idea is to try and break the ones that don't make any sense. So principles, I've just tell you that Bob warned me that he was going to ask me this question, but the answer popped into my mind. And I think it drives out of this talk that when you have an idea, and it's not a great idea, try taking a nap rather than action. Because as I look around where we are right now, vandalism is throwing a brick through a window because you can. And what I see in our society is inverse vandalism, which is making things just because you can. So most of the things that are made are, if you go to a flea market, you get a strong sense of this, that it's unbelievable to realize that almost everything in that flea market, some one or two or N people had to desire it so much that they went through the labor of designing it and building it and putting it out there. And so I think the idea of, especially in computer science, where the incremental change is kind of the black hole of every programmer, I think much more design before the programming and much more elevated view of what's trying to be accomplished, given that nobody's figured out a way to put a half-life on code, tends to stay around. And I believe that my friend Bill Buxton is going to talk quite a bit about the importance of design in the next talk. Thanks.
Thanks very much.
Thank you.
Thanks, Alan.